Students, we are back with another lesson. In this lesson, we'll continue with the spectral series of hydrogen atom. So up till now, we have derived the energy expression for the electron in the nth orbit. This is the energy expression. After this, we have derived the wave number. The wave number for the transition from a higher orbit n equals to 2 to a lower orbit n equals to 1. So this expression is for your wave number, and this term R represents your Rydberg constant, whose value is 1.0973 times 10 to the power 7 meter inverse. Fine. So now, using this wave number expression, we will discuss various spectral series which are produced by a hydrogen atom. So the first series is your Lyman series. So in this figure, can you see? This represents your n equals to 1 orbit. When an electron makes a transition from n equals to 2 orbit to n equals to 1 orbit, it releases some energy. Can you see? Similarly, if this electron makes a transition from n equals to 3 to n equals to 1, then also it releases some energy. Similarly, if it makes transition from n equals to 4 to n equals to 1, then it releases some energy. Similarly, from n equals to 5 to n equals to 1, again it releases some energy. From n equals to 6 to n equals to 1, it releases some energy. Similarly, from n equals to 7 to n equals to 1, n equals to 8 to n equals to 1, n equals to 9 to n equals to 1, it releases some energy. Okay, and when you produce this energy on a screen, okay, this part represents the screen. This energy is generally shown at this point of the curve. So can you see the one inside the red box? This represents the energy which is coming out from this transition from n equals to 9 to n equals to 1, n equals to 8 to n equals to 1, n equals to 7 to n equals to 1, n equals to 6 to n equals to 1. Fine. So this kind of series, can you see the small white line which are obtained on this black screen? This kind of series where the electron makes a transition from a higher energy level from n equals to 2 and so beyond. Okay, when it makes a transition from a higher energy level to a lower energy level, this is your lower energy level, and this lower energy level corresponds to n equals to 1. So when an electron makes a transition from higher energy level to n equals to 1 energy level, in that case, what kind of series we'll observe? We will observe Lyman series. And the energy which is emitted generally forms in the ultraviolet region, UV region. Fine. So if you want to find out the expression for the wave number, what you can do is you can use this relation. Write this relation: mu bar equals to R times 1 upon n1 square 1 upon n2 square. n2 square is the higher energy level, n1 square is the lower energy level. So mu bar equals to R 1 by n1 square. In this case, all of the transitions are done till n equals to 1. So what you do, substitute 1 here. So it will be 1 square. This is your lower energy level. And what are your high energy levels? The high energy levels are 2, 3, 4, 5, 6 and so on. Fine. So this is your n2 square, higher energy level. Fine. So this is your Lyman series when there is a transition from a higher energy level to a lower energy level, and the energy emitted will form in the region of the ultraviolet region. Fine. Now similarly, consider your next series. This is your Balmer series. Now whenever there is a transition from a higher energy level to your second energy level, right? So in this case, now instead of going to one, the electron is making transition to the second energy level. Now when the electron makes a transition to the second energy level, the energy emitted, can you see? This is the energy emitted. It appears to be a red light when the transition is from n equals to 3 to n equals to 2. When the transition is from n equals to 4 to n equals to 2, the light produced is somewhere in the blue light. Now from n equals to 5 to n equals to 2, the light is somewhat between, it is dark blue, fine. When it is from n equals to 6 to n equals to 7, it is purple. When it is n equals to 7 to n equals to 2, then it is a more darker color, fine. So in this case, where there is a transition from a higher energy level to your second energy level, you obtain the light in the visible region. Visible region means the light which you can see. Can you see? Like in this case, you can see the red light, in this case blue light, then you have light blue, then you have purple, and so on. So in such kind of spectral series where there is a transition from a higher energy level to n equals to 2 level, in that case what happens, the emitted radiation, this is your emitted energy, it falls in the visible region. So such kind of series are known as your Balmer series. Fine. In such kind of transition, what happens? The transition is from higher energy level to your n equals to 2 energy level. Fine. And in this case, the energy emitted falls in the visible region. So if I use the wave number formula, what you do? The transition is from a higher energy level, n2 whole square, where n2 can be 3, 4, 5 and so on, to n equals to 1, to n1 equals to 2. This is your lower energy level. In this case, how much is the lower energy level? 2. So here n1 will be equals to 2. So this is your Balmer series. Fine. Now similarly, the next one is your Paschken series. So in case of your Paschken series, the transition is from higher energy level to the third energy level. Fine. It can be from n equals to 4 to 3, n equals to 5 to 3, n equals to 6 to 3 and so on. Fine. So this is your Paschken series. Fine. In this case, the transition is from the higher energy levels, from the 4 pi 6 and beyond to n equals to 3 level. Fine. And when the energy is emitted, in this case, when the energy is released, it falls in the infrared region. So this is the wave number formula for your Paschken series. Fine. Now similarly is your bracket series. Now in case of bracket, this time what happens? The transition is from higher energy levels to your fourth energy level. Fine. So it can be from 5 to 4, it can be from 6 to 4, it can be from 7 to 4, 8 to 4, 9 to 4 and so on. Fine. So this spectral series, can you see? These lines which are produced, this represents your bracket series, where there is a transition from a higher energy level from 5, 6, 7 to n equals to 4 energy level. Fine. So you substitute the value of 4 here and then you can find out the expression for the wave number. Now after bracket series, the final one is your P-fun series. Now in this case, what happens? Now in this case, instead of making transition to n equals to 4 level, here the transition will be till n equals to 5 level. And in this case, you will see this spectral lines. Okay, can you see the ones which are shown here? These are the spectral lines produced. This corresponds to your P1 series, where the transition is from higher energy level to your fifth energy level. Fine, so you can substitute the n1 equals to 5 in the wave number expression here, and then you can find the corresponding wave number. Okay, now in this case the emitted energy will be in the region of infrared. Fine, so these are the 5 spectral series. For the 5 spectral series, what you have to remember is from where, what is the high energy level, from where the electron is making transition to which energy level. This is important. Next, if the energy is making transition, what kind of energy it is giving out. It is giving out ultraviolet, visible. Okay, it's very simple to remember. For Lyman series, okay, for the first kind of series it will be ultraviolet. For the second series, that is your Balmer series, it will be visible series. Rest all of the series will give the energy in the region of the infrared region. Fine, this is your second point. The next point is that you should know how to calculate its wave number, this mu bar. If you know how to calculate the wave number, then you can also find its wavelength, frequency and other related physical quantities. Fine, so these are the 3 important points which you should remember for your spectral series. Fine, so that's it for today's class. Thank you, and if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.